must have seen UIs like this in Siri, Gemini, and many other AI applications. But have you actually wondered how they are built? What's the calculation behind this amazing animation, and how you can actually build one yourself? So, if you're as curious as I am, stay tuned and you will actually be building one yourself by the end of this video. So, yeah, let's go. Okay, so let's start with the understanding of how this globe is created. So I've created a very simple presentation so that you can have a clear picture on what is going on behind the scene. So this is the flow, very simple flow. I've kept very simple 5 classes and no architecture or anything as such, nothing complicated. So first, the main entry point that we have is the main dot dot. Okay, so there's nothing in main dot dot. We are directly calling the speech input class. Okay, now once we call the speech input class, this class basically handles all the UI related tasks, and what you see here is basically part of speech input, the output of speech input class. Okay, now this speech input class, we'll dive into it, but it mainly consists of 3 main other classes. So the first one is sound envelope. This will process whatever audio that we put in, like whatever we say, it will process that and accordingly move the orb. Okay, I'm gonna call it orb for now. So, and the pixel dust. So the pixel dust is basically the animation that you're seeing here. This animation is all in this class. Okay, now the last one is the entity dot, the dust entity. So this dust entity is basically a model which has all the characteristic of a particular particle. Okay, so let's say for example this particular particle, right, this particle, all the characteristic will be listed here. Okay, so this entity is what is going to drive the characteristic of this whole the list of particles here. Okay, I hope you understood that. Now let's go over the next class. So let's start with dust entity. Now the dust entity consists of all these fields, and we'll quickly go through what each field is supposed to mean. So theta and phi, they are the longitude and latitude of that particular particle. Okay, don't overthink this, because if you overthink this it will be too complicated. So I'll just try to make it as simple for you. So let's say for example this is the particle. Okay, now this particular particle will have to start somewhere. It needs to have a location in the globe, in the orb, right? So in this orb, a particle needs to start from somewhere. So that longitude and latitude is provided by theta and phi. Then next is radius at y. It is basically the ring radius, right? This ring, right? A particle needs to go through a particular ring. It needs to follow a particular path, right? That ring radius is what is the radius at y. So for each particle, if you think, right, it has a starting point, it has a radius, right? So we have defined its starting point, its path, and next the face. So if you see, there is a wobble in each and every particle. It goes a little up, then down, then up, to create this magical effect, right? So this effect is provided by the face field, okay, or the face parameter. Okay, next is the base size. So if you have noticed, each and every particle has different size. Some of them are big, some of them are small. So all these particle sizes, again, they're random, and we have made it in such a way that each and every particle size are like different. They don't, so a particular region does not consist of only a particular set of size. It's just randomized everywhere. So for that reason, you will get to see the school effect, right? And the last is we have the color. So mainly I have taken two colors. You can add in more colors if you want. Okay. So here I've taken like the brown color and the yellow color, but if you want, you can take more colors. Okay. Now this is what actually the dust entity is all about. We will come to the golden angle a little while, but let that sit in. Okay. We are done with the dust entity. Next, we are going to go for the speech input. Why? Because here the main method, which is generate particles, this method is very important because this method will actually um, help us create the characteristic of each particle. Okay, so earlier I've explained you a few things. Um, let's map that down. Okay, so particle generation, right? Golden angle, I'll come in a little while. So basically that is 137 degrees. Okay, but you know what, let's dive into the golden angle. So if you can see here, right, we have two different orbs. Here the particles are not distributed properly, and here the particles are distributed very uniformly. Okay, how is that happening? When we multiply the location with let's say 45 degrees or 90 degrees, it comes into clumps like this. Okay, but if we multiply it specifically with 137.5 degrees, right, it distributes itself uniformly. This 137.5 degrees is actually inspired from nature. If you see the sunflower, the cone, they have a very similar pattern. So, and they are uniformly distributed. So all that is actually a particular angle, which is 137.5, and hence it's known as the golden angle. Okay. Now, okay, the count is, I have kept here 300, but you can keep more, you can keep less, it's all on you. Then we have the golden angle. So this calculation, right, it's basically 137.5. You can actually replace it if you want, but we are just going on with the formula here, right? We're going with the formula. So let's go with the formula and uh, let's calculate the rest as well. Okay, now if you have noticed y here, it's actually the phi, but a sine of phi. It's like an angle of y. Okay, and this y is also calculated according to the I. So since we have kept the maximum count as 300, it's going to go from 0 to 300. So each particle will have its own I value, right? So that will make this y unique. Okay. Now whatever y that we have chosen, right, that will also define radius at y. Okay, because each y is unique. Okay, and as you can see here, for theta we have directly multiplied the golden angle with I. Okay, so I hope you understood that. For theta, we have the theta value now, so it is going to have its own longitude, 5 its own latitude, radius at y, at which side of the sphere, like at which height of y is that particle going to appear. We have the phase where we have randomized um, the wobble, right? And it's a small value, not a very drastic value. Okay, all this you can print out and check so that you understand what exactly is the value that's going on, but right now I'm not gonna do that. Now then we have the base size. So if, as you can understand from this formula, we have 1 as the minimum and the maximum as 3 plus 1, right? And anything in between is what we are like adding. So 1, 2, 3, 4. Okay, and all these numbers will be random. Okay, then we have the colors. So as you can see here, I have randomized between these two colors, right? Yeah, so whatever you saw here, we have added it here. Now let's go with the second one. I think I've already explained this. So let's go with the next class, which is the pixel dust. Okay, now pixel dust has a lot of formula, but I would say like don't like think too much into the formulas right now, because we are more concentrated on how to produce this UI, right? And to just understand the basics, so that at least if you have to change something, let's say add in more wobble, add in more particles, add in more different angles, or like whatever, you know where to change, right? So if you have to change the color, you know where to change, correct? Okay, so here I think the formula is pretty simple. We are trying to get the center of the orb. This base radius is the smallest sphere that we are planning to make. Let's say when you say something, you want the smallest sphere to be of that particular size, for example. So here we are taking 25%, but you can add in more if you want, right? And then we have the like sphere radius. It will change according to the level, and I've added extra a little bit of buffer here and there. You can change accordingly. You can even remove everything. It totally depends on. Now we have the glow paint. So glow paint is basically the inner glowing circle. If you see, that is the glow paint. Okay, so I am creating that glow paint because I feel like if I just add only the particles, it wasn't looking that great, I would say. So I added the inner globe that will make it look as a whole, right? So there's nothing like major calculation happening here. It's just the colors, and we're just drawing the sphere, very simple sphere with draw circle, right? Canvas or draw circle, and also little bit of gradient to help it look like a 3D sphere. Okay, now comes the main part, the dust particles, right? So just keep in mind that right now we are just trying to map the 3D position, okay, of each of them. Okay, so this formula is basically for mapping all the particles in its 3D position. Okay, and now the next important thing is the depth and the perspective. The depth is basically what is going to make it look like a 3D effect. So okay, observe carefully here, right? The outer layer that you're seeing as a front view, right? That front view has more bigger size of the particles. Okay, and if you see the the behind view, right, it will look like the behind view is moving more further away. That is because we are resizing the particles to create the depth effect according to the value that is the z-axis. Okay, according to z-axis we are pushing it back and forth. Okay, to explain it more better, we have this UI. I think I hope this helps a little bit. So this whole one particle, right, the one particle rotation is 20 seconds rotation overall. Okay, I've already explained there are 300 plus, I mean there are 300 particles, but you can add more particles if you want. right? The depth is basically the perspective, the formula that you saw here, that's exactly the formula that's here. But what I wanted to show more is on the Z depth scaling. Okay, so if you see here, this is more smaller and this is more larger. This is more brighter and this is more dimmer. Okay, and how are we calculating that? Basically, when Z is equal to 1, we are making that bigger, and when Z is equal to minus 1, we are making it smaller. Okay, it's just the formula, and according to the formula, we are making it bigger and smaller, and hence creating this 3D effect. I hope you understood that. Okay, so once you have understood this part, the next one is the wobble. So wobble I've already explained to you. Basically, whatever the value that we pass down, we are calculating where and how that wobble should be shown. Okay, and all these we have already discussed on how we're getting all these values. But at the same time, again, this is something that you can change the level. Okay, so according to the level, which is the sound level, right, as I explained earlier, from 0 to 1 the sound level will be coming, and this wobble will happen more when we have higher level and lesser when we have lower level. Okay, so that is all about the wobble. And we have, so this basically is what is happening. It is projecting each and every particle that we have just calculated earlier, with everything wobble, perspective and all that, and then we are providing a particular location. Okay, this is the 3D coordinate, okay, where it should appear. Okay, now once that is done, here will be the radius and here will be the opacity. Okay, these two, I think you understood. We are using it to create a depth effect and to make it look more visually appealing. Rest is all a draw circle, which is a method to draw all the particles and a little bit of blur. So I have added a blur to each and every particle, but if you don't want the blur to happen, you can just remove it. Okay, and it will look something like this. So it all depends on you. I like it with blur, but totally depends on you. Now that we are done with pixel dust, let's go ahead with the sound envelope, which is again another most important part of this project. So sound envelope class has lots of things going on as well, but to help you understand a little bit better, I have created this graph. Okay, so let's start with the first portion of the flow, which is a safety gate. So safety gate basically removes the possible plus minus infinity or any n signals. Okay, so we are looking at a very finite value like 10 dB, 20 dB, not minus 10 dB, not minus 20 dB, nothing like that. Okay, and also we are making it absolute. So whatever the value is, right, we are making it a finite, like we are just checking if it's a finite value or not. Once it's finite, we are making it absolute, so that if there's any negative value, we are going to remove that. And then after that, we are going to also add a default value, because sometimes if this comes as any n value, then we are going to make a default value as 0. So what is save value actually? It is just taking the raw value, which is the voice that we input, right? So whatever, after pressing here, whatever voice that whatever we say, that will be recorded as a raw level. And that raw level is what we are going to furnish it down and make it into a safe level. Once safe level is done, we are going to check if it's less than the noise floor. Now, what is noise floor? Noise floor and peak floor are the minimum and maximum sound in a room. Okay, so noise floor is basically, like, by default we can keep it 0 because we are thinking it's a fully silent, no sound room. Okay, so 0 dB room, and we are keeping a peak floor of 10 for now. But again, if you want, you can adjust it. Anyways, this formula will be adjusting it accordingly. Okay, so if the safe level is less than noise floor, which, let's say, it is not um, it is not 0, for example, it is like 10 dB, for example, right? So after filtering safe level, we have 10 dB, it is not less than noise floor. So the new noise floor will be updated. How? We'll be taking the 98% of the noise floors, plus we'll be taking 2% of safe level. So what in this case, what are we doing? We are trying to increment the noise floor a little bit because we think the environment is not fully silent. Okay, but we are trying to take minimum because we have to make sure that the noise floor is minimum. The minimum sound in that room is the one that we assign to noise floor. Okay, next let's see the peak floor. So in peak floor, what happens is we are going to take 99% of the peak floor or the safe level. So in this case, what happens is we have 10 dB safe level and 10 dB peak floor, right? So it's either 99% of that, which is a little less than 10, or 10. So we are going to take 10 as the peak floor. So mind you, if it was 20, then the 20 will be the next peak floor. So in short, what is peak floor? The highest recorded value is what the peak floor will be. Okay. Now, sometimes what happens, and it's very rare, sometimes what happens, both peak floor and noise floor end up being the same. Let's say peak floor is 10 and noise floor also is 10. So in that case, both of them, like 10 minus 10 will be 0, right? But we don't want to keep the reusable range as 0. We want to keep the range to be at least 5, because why? While doing normalization, that 0 will be divided here, and that will cause an infinity. So we don't want that, right? We don't want the app to break. So for that reason, we have kept a minimum of 5, so that in case, right, rare cases, but in case these two end up being the same and the value turns out to be 0, we have 5 at least. Okay. Now once 5 or whatever the value will be here, that is taken, so we are just normalizing it. We are just, making sure that the new level that we have, and that too we are clamping it from 0 to 1 in order to understand the range. A range from 0 to 1 so that we can visualize it. Okay, so that's why we are clamping it between 0 to 1. Now next is, if the normalized level it's very low, like if it's lesser than 0.03, we are going to make that to 0. We don't want to show a wobble for such a small range, right? For the target level, what happens is, whatever the normalized level that we have, right, we are just giving a little bit of boost if required, right? And the power of this into, like, to the power 0.75, it's pretty less, like very less. Let's say if it's like 0.12 with little bit of this target level, we are adding a little bit of points like 0.1, 0.12, like that. Okay, so I dry run it and I understood that it's just giving a little bit of boost. Okay, but at the same time, if let's say if this normalized level is 0 or very close to 0, it will help in bringing it down to 0. So it will, so what this formula will do is it will help in releasing fast, okay, and exponentially increasing it. So let's say if I keep on saying then it will very small, like in very small view it will be shown, in very small value it will be increasing, but the moment I stop speaking it will drastically decrease. So this is called the attack and the release. I'm not sure if it's here. Okay, yeah. So the attack and the release mode. Basically, when we say something, it will slowly increase, okay? But when we stop saying, it will decrease exponentially. Here also, we are just checking if the previous one, if the target level is greater than the previous one, then we are taking little bit percentage of the previous and little bit percentage of the target, and that will be the new value that will be returning, okay? And if it's less than that, we'll be just taking little bit percentage of, previous, and like the 50-50 percentage of both previous and target. Now why do you have to understand this formula? This will help you to calibrate. Let's say if you want it to make it drop more faster, you have to adjust these values, okay? Right now I've kept it 50-50 because I felt like that is what made it look more good, but if you think you can improve it better, maybe this is the formula that you have to play with. I hope you understood this concept. If you want the full source code, the link is in the description below. And if you think this video was useful to you, do leave a like because it helps the algorithm. And do subscribe to my channel because more videos like this will be coming. And if you don't know, I have taken up the 90 days challenge where I post one video per week. So yeah, stay tuned and see you in the next one. Bye bye.